Hi everyone. We will now begin with our discussion on the frequency response of cascode amplifiers. Now this lecture on cascode amplifiers, I have divided it into two parts. The first half of the lecture, we will look at, in a qualitative fashion, we will look at the history or the history of development of your cascode amplifier. So I'll roughly look at what happened, how engineers chanced upon this cascode amplifier structure when they were trying to fix the problem of low bandwidth in vacuum tube amplifiers. Shown here is a 3-terminal vacuum tube amplifier. So the 3 terminals are anode, cathode and the grid terminal. They are equivalent to drain, source and gate terminal of your MOS device. Now just to quickly refresh your memory, the basic principle of operation of a vacuum tube amplifier is such: a cathode terminal is heated sufficiently, and when it is heated, it starts emitting out electrons. So we have a cloud of electrons formed above the cathode terminal. Now this process is called thermionic emission, and these electrons will be drawn towards another plate called anode if the voltage at the anode plate is greater than the cathode plate. So when these electrons reach the anode terminal, we have a current flowing from anode to cathode. So this current, I have written it as IA, called the anode current. Now by applying voltage on the third terminal called the grid terminal, we can control the flow of current between the anode and cathode. So IA here can be controlled by an appropriate voltage at the grid terminal. And we said this is like an amplifier operation. So any 3-terminal amplifying device, we can control the flow of carriers between 2 terminals by an application of voltage on the third terminal. Now we look at this vacuum tube amplifier and we will try to understand what was the problem that engineers were facing as far as bandwidth is concerned. So shown here is a vacuum tube amplifier configured as a voltage amplifier. The cathode is grounded, anode is at a higher potential, the DC voltage is not shown here, the biasing is not fully shown. Anode here is at a higher DC voltage, and we are applying the signal on the gate terminal, on the grid terminal. The voltage signal has a finite source resistance, and we already discussed that the finite source resistance models the finite power delivering capacity of the voltage source. Large voltage source generally means the amplifier can deliver very little power. The voltage source can deliver very little power. So this configuration is called the common cathode configuration, because cathode is at the output is the common terminal, input is at the grid terminal, output is at the anode terminal. Now, like a MOS device, even a vacuum tube amplifier suffers from parasitic capacitors. So we have capacitance between the grid plate to the cathode plate, then we have a capacitance from the grid plate to the anode plate. Now this capacitance between grid and the anode plate sees a huge voltage across it, because this common cathode amplifier or this vacuum tube amplifier is going to amplify this input signal Vs by a really large value. I'm going to assume, like a MOSFET, we can define transconductance for a vacuum tube amplifier as well. So I'll call Gm as the transconductance of this vacuum tube amplifier. And if you apply a voltage Vs here, and I'm going to neglect the gate current, the grid current drawn into the grid terminal. So then this can be approximately written as Gm times Vs at low frequencies, and the gain of the circuit will be minus of Gm times RL. So if you look at this capacitance CGA, so I'm calling it gate to anode capacitance, a grid to anode capacitance. On one terminal the voltage is Vi, on the other terminal of this the voltage is minus of mod A times Vi, where mod A here is Gm times RL. Now this capacitance has to be charged to a really large value. It has to be charged to eventually you'll have to deliver a charge equal to the capacitance CGA times the voltage across it, which is 1 plus mod A into Vi. Now the input voltage which this node here, the grid node, is going to be charged to, let me call that as, eventually in the steady state it will be close to Vs, or here this is Vs here, eventually it will be charged to Vs, but the input voltage source, because that's the only path by which you can deliver charge to the capacitance, it will be delivering a charge of this value, which is CGA into 1 plus mod A times Vs. Since it's delivering a huge charge, it's going to think that it's going to see a large capacitance as the input. As far as the input is concerned, it's just going to charge this node to Vs, but to charge it to Vs, it's delivering a charge of Cga into 1 plus mod A times Vs. So it's going to look like an apparent capacitance or an effective capacitance at the grid terminal of value Cga into 1 plus mod A. Now this large capacitance is going to create a low frequency pole at the input terminal. So we'll have Cga into 1 plus mod A. This is going to create, this RC network is going to create a low frequency pole, and that's going to decrease the bandwidth of your system. So shown here is the frequency response of a common cathode amplifier. DC gain, I've only shown the magnitude, which is 20 log of GMRL, and the pole here occurs at 1 by Rs into Cga into 1 plus mod A. Even though Cga, the gate to anode capacitance, may be small, it's getting multiplied by a huge value. If gain is say 60 decibels or A is 1000, it's going to be multiplied by 1000 times, and therefore the bandwidth will be reduced significantly. Now this was the problem that engineers were facing at that time. Now to solve this problem, you have to first see what is the source of this problem. The source of this problem is the huge voltage across this capacitance Cga. So the next step in the thought process is to see if by some means the voltage across this capacitance can be reduced. If by some means this input on one terminal is the input signal, so that we cannot do anything there. But the other terminal, can something be done to the other terminal? So that's what that thought process led to a device called the tetrode, or the 4-terminal vacuum tube amplifier. So in that, what they did was they introduced another terminal called the screen grid terminal. So this is like a grid terminal, but the voltage at this terminal is fixed. It is fixed to some DC voltage. I'm calling it VSG, that's the V screen grid terminal voltage. It's fixed at some DC voltage. The moment you do that, that's going to screen the anode. So you have anode and the grid terminal anode here. In between, we have introduced another terminal called the screen grid. And now this is held at a fixed potential. So the AC variation here is 0 because the DC voltage is fixed. The screen grid plate is connected to a fixed DC voltage. The small signal variations on that plate will be 0. So therefore, that node is at AC ground. So you have any field lines starting from the gate terminal because of the input voltage are going to end on the screen grid terminal. Essentially, the screen grid terminal is screening. It's behaving like a screen between anode and the grid terminal. So therefore, you will only see a fixed capacitance between gate and screen grid. So I'll call it CGSG, the gate and screen grid capacitance. So that's the capacitance that will be seen here. So here I'm showing 4 terminals. It looks a little cluttered, probably. So here this terminal here is the grid terminal. This is the screen grid terminal. So you will have a fixed capacitance between the two. This node voltage is fixed. So therefore, at the input, you are only going to perceive a capacitance of CGSG. So this is your grid to screen grid capacitance. Now in the same amplifier, we have solved the problem of this capacitance multiplication. So this effect was called Miller effect because this capacitance is getting multiplied by a huge value, which is reducing the bandwidth. But now if you see here, by introducing a third plate, we could solve that problem. Now this capacitance is no longer getting multiplied because on one side it is fixed. At the other side you have an input voltage, so the total voltage this capacitance has to be charged. The small signal voltage it has to be charged to is Vi itself. So therefore we solved that problem of Miller multiplication, and this we could extend the bandwidth using a tetrode. But a tetrode came with another problem. The screen grid voltage was at a higher voltage, is held at a higher voltage. Now if you recall, the fundamental operation by which a vacuum tube amplifier works is that you have the cathode terminal, electrons are energized, and these electrons hit the anode terminal, and then there is a path for the current through the load and all of that. But since these electrons are very high energy electrons, especially if the anode voltage is very high, you have a strong field between the cathode and anode, these electrons will be accelerated to such high speeds that they can knock off some electrons from this anode plate. So these electrons are called the secondary electrons. So these electrons, the secondary electron were emitted because of these high energy electrons going from cathode to anode. Now these secondary electrons, they were now drawn towards the screen grid terminal because that was held at a higher voltage. They were drawn towards the anode, the screen grid terminal, which means now this anode plate has lost some electrons. Now remember, what constitutes the anode current is the total electrons which are going to go from cathode into anode. That's what is going to constitute the anode current. But if the anode is going to lose some electrons, the anode current will decrease. So this is an interesting phenomenon that they were observing. If you increase the anode voltage, there was a decrease in the anode current. So anode current was slightly decreasing. That's because of this emission of secondary electrons. This decrease in anode current because of an increase in voltage can be seen as a negative resistance. And we know negative resistance can create right of plane poles, or when used in resonant circuits, they tend to create growing oscillations, which means the system became unstable. So that was the problem with the tetrode, is that the second emission of secondary electrons was causing instability. Even though it fixed the problem of bandwidth, it introduced a new problem because of the secondary electrons, which are emitted from the anode terminal. Now to fix that problem of secondary electrons, what they did was that they introduced one more terminal in the vacuum tube amplifier. They introduced another terminal called the suppressor grid. Now this terminal was held at ground or at a very low potential compared to the anode. Now because of which the secondary electrons that are going to be emitted from the anode, because this is at a lower voltage, they will be repelled back to the anode plate itself. So that was somehow controlling or reducing the emission of the secondary electrons. So normally the suppressor grid was often connected to the cathode terminal. So this device was called as pentode because it had 5 terminals, 3 grid terminals and 1 anode and cathode terminal. So oftentimes it was also called the triple grid vacuum tube amplifiers. Similarly, a tetrode was called the double grid, and the conventional triode was called as the single grid vacuum tube amplifiers. Now this pentode fixed the problem of bandwidth. It also solved the problem of secondary electrons, but this was actually more noisier than a conventional triode amplifier. So that's when in the year 1939, a very famous paper on voltage stabilizers was written by Frederick Hunt and et al. In 1939, where they were talking about voltage stabilizers, and in that they were exploring many possible ways of connecting triode amplifiers, the single grid triode amplifiers. In one such configuration, they took the anode of a common cathode configuration and fed it to the cathode of another amplifier. So this is cathode here, this is anode. They fed the anode of the first amplifier to the cathode of the second amplifier. Conventionally, anode goes to the grid. So we had the amplifier, the anode terminal will go to the grid of the next amplifier. But now this anode was instead connected to the cathode, and by doing so, they were observing that they could fix this problem of the capacitance multiplication, which is the bandwidth could be extended significantly, and it was not as noisy as pentode. So that's where the name cascode comes from. It's a cascade of an anode and a cathode to distinguish it from a conventional cascade of anode going to the grid of the next vacuum tube amplifier. Though I have not found any good source for this, the reason for the name, the nomenclature, but I found this on the internet. One of the reasons for cascode, the naming of the cascode amplifier, is cascaded triode amplifier having characteristics similar to but less noisier than a single pentode. It gives you all the benefits of a single pentode, which is extended bandwidth, no secondary electron emission, but It also comes with lower noise. Pentodes we just discussed was high in noise, but this was lower in noise as well. That's the advantage, and that's where cascode amplifiers saw its genesis. Shown here is the frequency response graph for a conventional common cathode vacuum tube amplifier. In pink, that's what I've shown here. The gate to anode capacitance is getting multiplied by 1 plus mod A. Whereas in a cascode amplifier, I'll probably derive it rigorously in the next part of the video, in the next part of the lecture. And we will see that multiplication will not be that bad. In fact, the capacitance that will be seen at the input will just be twice of the gate to anode or the gate to drain capacitors. So the bandwidth gets extended significantly. This was the reason why engineers went from chanced upon a cascode amplifier mainly to extend its bandwidth. So one thing that has to be kept in mind here is that the DC gain is still the same because we are now driving a resistive load. The DC gain is still the same, but the main advantage here is the increase in bandwidth. The bandwidth is increased considerably by going for a cascode amplifier, especially if the source resistance is very large. That's what is creating the pole here. For large source resistances, it gave a huge benefit. So the points to keep in mind here is that we started with vacuum tube triode amplifier. We saw the problem of capacitance multiplication. We went to tetrode, which fixed it but introduced a new problem of secondary electrons emitted from the triode, from the anode terminal, and that was making the amplifier unstable. Then we went to pentode, which fixed both the problems. Secondary emission was fixed and bandwidth was also fixed. There was no longer a multiplied capacitance, but it was more noisy. So to solve that, finally we settled on to the cascode amplifier structure, which combined the best of all this. It offered a high bandwidth, and it also there was no secondary emission of electrons, and it was also less noisier than a pentode. So that's how the history of cascode amplifiers. That was the history of cascode amplifiers. The next lecture, I'll try to argue from a circuit point of view, how can one arrive at a cascode structure starting from a common source amplifier. Now mind you, a very important thing to notice here is that when cascode amplifiers were invented first, they were not invented for very high gain. Of course, even common cathode was giving a high gain. They were mainly invented for high bandwidth. That was the main benefit, or the claimed benefit of a cascode amplifier. We will see in the next lecture that cascode amplifiers in today's times for low frequency circuits are used for high gain as well. And under what conditions, we will see all those things in the next lecture.